David, how are you? Yes,
No, because this PDF was scanned like this. Okay, yes, you can do it. Yeah, but I didn't check it before printing. Then I realized, oh, I have to choose the print differently. Yeah, that's it.
We continue today with the local magnetism. More or less repeating in more detailed scheme, which we quickly performed yesterday with the semi-classical theory of magnetism. Any problem in understanding what we did yesterday with the superfluidity? Sorry, I said yesterday, but of course I meant Friday when the bus strike happened. So yesterday we finished with superfluidity, and any questions regarding that? Please.
You said superconductivity is superfluidity of copper pairs in some sense?
In some sense, yes, but you should, Professor Yevtushenko will tell you more. But in principle, when we speak about superfluidity of bosonic system, the bosons are well defined. I mean, the size of boson, is much smaller compared to the distance between them. So we were always discussing that situation, that this is A, this is 1 over n to the power 1/3, and we have n, A, Q much smaller than 1 as a measure of interaction. This is what A is the size of boson. When we will be speaking about Cooper pairs, it's a completely different situation. It's a situation of that sort. So the size of Cooper pair is a correlation length psi. And you will see it from the microscopic theory of superconductivity that you are in opposite limit. Therefore, in some sense, it's quite vulgar to speak about superconductivity as superfluidity of Cooper pairs. However, it's in fact superfluidity because the superconductors conduct electric current without energy losses, and on the other hand, the excitations are Cooper pairs. So I would say that superconductivity and superfluidity are closely related phenomena, but one should not understand it as one-to-one correspondence. This cartoon, which I just show you for comparison, tells you the main difference between two limits. And of course, Cooper pairs are charged particles. Electrons, the charge of Cooper pair is twice the charge of electron, and the reason two charged particles to attract is existence of mediating electron-phonon coupling, which makes this attraction possible. But of course, there is always Coulomb interaction, so two negatively charged particles always repel each other. So in order to have superconductivity, and one needs to have balance in favor of attraction. And again, it's impossible to speak about Cooper pair as a bound state of two electrons, because bound state is bound state of two particles, for example, can be formulated mathematically as existence of pole of the scattering amplitude on negative axis of energies. This energy corresponds to the bound state, as you know it from quantum mechanics. How advanced was your advanced quantum mechanics, by the way? Did you have a scattering theory?
No.
That's good. Then what Gunesh will do with you on Schrödinger equation scattering theory and green function formalism will be useful. But I'm afraid that if you don't know at all scattering theory, even basics of scattering theory, it would be difficult for me also to speak about transport, because transport is based on the fact that there is a scattering. So my statement about poles of scattering amplitude as a function of energy, of course, sounds as nothing for you. Well, if we go to potential, some kind of potential. So the bound state, this is u as a function of x, and this is the origin, well, r, for example, typical. So the bound state and continuum so these are bound states of potential. So these are continuum states of potential. So the particle can escape to infinity while the particle sitting here cannot escape to infinity because it feels the potential. So again, we discussed it in superconductivity. A copper pair is not a bound state in some sense. It's a collective state. Therefore, language about isolated Cooper pairs is not appropriate language in some sense. So the superfluidity of Cooper pairs being understood as a collective phenomenon where many Cooper pairs are involved and would be more correct definition, but as I said, superfluidity and superconductivity are two closely related phenomena. Although there is also a difference between Bose gas and Cooper pairs.
But I think in the case of helium-3, they are the same.
Helium-3 is a fermionic system, right? Therefore, the superfluidity in fermionic system has the same mechanism as a superconductivity, because fermions should form something which is bosons. Fermions cannot possess any superfluidity because of Pauli principle. So first, some boson should be formed as a composite boson, and then this composite boson some way should may superfluid. Helium-4 is bosonic system. Unfortunately, your lectures overlap with seminars. Today was a very interesting seminar by Professor Schreck from Innsbruck, experimentalist, who was talking about experiments in cold gases. It was in CIS at 11 o'clock. So maybe I asked Patrizia to try to correlate your schedule with the seminar schedule, although I think it's a complicated task. But still, whenever you have time to come to seminars, please do it. Both CISA seminars and ICTP seminars on condensed matter physics are very, very good. We invite leading experts, leading world experts, both doing experiments and theory to discuss the real frontier of research, and you can learn more, and moreover, you can see the usefulness of the knowledge you get in lectures. So then you can judge what you understand more, what you understand less, what kind of questions are to be discussed in more details. And also seminars is the real life of scientists. It's our blood, so to say. We need to learn what other people are doing. We, of course, and this is how community is organized. Of course, one can say that there are magazines, journals, and one just reads a paper, but you may see, even reading an archive papers, there are hundreds of papers appearing every day. and it's simply impossible to trace what's going on. So seminars is one of very efficient mechanism which allows the circulation of knowledge. Yeah. So please don't feel yourself as being, say, students. Feel yourself as being young researchers. And to be young researchers means to participate in scientific activities of institutions. You are very much welcome, and this is also part of your education. It's a part of education of everybody. We are all learning something during all our life, and this is why our profession is so nice and good. Okay, more questions. Then I come to magnetism. Yeah, and we spent several lectures. So, quick reminder of what has been done on Friday lecture for those who were absent. We started to discuss simple models to describe magnetic state. What is magnetic state characterized by? We are talking about systems of local moments. So we have in mind a lattice of crystalline lattice and atoms occupying the lattice sites possess spin, for example. And for some systems like iron, cobalt, nickel, it happens that these systems possess magnetization in the absence of applied magnetic field. So the systems are characterized by magnetization which exists. So this is uniform magnetization. For example, in z direction, z is arbitrary direction, z we choose in the direction of magnetization, so to say. This spontaneous magnetization appears at temperatures smaller than some critical temperature and doesn't exist at high temperature. You probably know from your child experience that if you take a magnet, maybe some of you like to play with a magnet in childhood. So if you take a magnet and warm it, not a little bit, but then making magnet hot makes it worse. So the magnet, which is warmed up, demagnetizes somehow. Of course, it's very difficult to notice it at the room conditions because typical temperatures in real magnets of the order of 300 Kelvin, is the order of 600 Kelvin, 300 centigrades. Therefore, one needs to make a cooker and put a magnet in a flame. Then one can see that it loses magnetic properties. But still, this is a fact that magnetization disappears when one comes to temperature higher than some critical one. So therefore, we said that this is a specific feature of magnets. It possesses spontaneous magnetization at low temperature and no magnetization at high temperature. So here we may think about state as disordered or paramagnetic, the same way as we discussed paramagnetic state in the electron gas. So the response appears only as a response to applied magnetic field, and if you apply some field, you will have magnetization roughly proportional to this field. However, here it's different. The system wants to be ordered, and what's naive vision of what's going on in the system, that at sufficiently low temperatures, all spins would like to look at the same direction, and this is why spontaneous magnetization appears in the system. So in order to cook some simple model for this theory of local magnetism. Local means the magnetism is associated with the atoms occupying lattice sites in crystalline lattice. It's not a magnetism of mobile electrons which can move in magnetic field because there is no kinetic energy in the system. So in order to hook up this theory, we first made very naive attempt saying that suppose our spin is big enough, so spin is much bigger than 1. Well, some system exists. For example, gadolinium, if I remember well, is characterized by spin like 15½ so 7.5, which is sufficiently big. And look at this spin in semi-classical limit as a vector living on a sphere. So we imagine some sphere. This was our magnetic moment, and we said another thing. We applied another assumption, saying that let's assume for the moment that spins or magnetic moments being semi-classical, and this is a condition for semi-classical treatment of the moment. And by the way, does the word semi-classic sound to you something? Did you study semi-classics in advanced course of quantum mechanics? Do you know what Bohr's Sommerfeld quantization rule is? In semi-classics, look, one has quantum well, whatever. If one is interested in higher levels, sufficiently high, then one may adopt approximate way to solve the Schrödinger equation using something which is known as semi-classical method. It's complementary to perturbation theory. However, it's based on the fact that your wavelength. So what happens if you are on a ground state? Your wave function is of that sort. If you are on a high excited state, your wave function has n zeros, where n is a number of excited states. So your wavelength is of that sort. So if your wavelength lambda is much smaller compared to the size of the system, one can treat system as almost classic and make expansion of your solution of the Schrödinger equation in terms of inverse, in terms of Planck constant. So you know, in the powers of Planck constant, so to say, one picks up the quantum nature of the system. So you don't hear anything about semi-classics? Okay. What did you do in advanced quantum mechanics? Perturbation theory?
Second quantization.
Yes, and then hydrogen atom, Stark effect, Raman effect.
What do you mean by the
Look, my advice, take your favorite book of quantum mechanics. My favorite one is Landau-Lifshitz. And read the chapter which is called quasi-classics or semi-classics. Read a few paragraphs. Because this is not only one among other tools. This is one of the basic concepts of quantum mechanics. And your education is very much incomplete if you don't know anything about semi-classics. As I said, the semi-classics works well if n is your principal quantum number is much larger than 1, or your wavelength is much smaller than the typical size of the system, or any other quantum number, for example, spin, is much bigger than 1. Why it is so? We come to the quantum mechanical treatment of spin. The spin is operator subject to non-commuting algebra. You know that the commutator of two components, Sx and Sy, is equal to Sz. So therefore, since spin is non-commuting variable, and presumably you had theory of angular momentum and you know what spin is, right? This is good. Then you see that if variables are non-commuting, like coordinate and momentum, what does it mean? That there is uncertainty, right? One cannot measure if commutator x and e is equal to constant, the variables are not commuting. It means that one cannot measure both coordinate and momentums simultaneously with arbitrary accuracy, because there is uncertainty principle that delta x, delta t is much larger than h bar in principle. That's a good exercise says that to minimize the uncertainty principle, one needs to take something which, you know what, a coherent state. And coherent state is a Gaussian weight package which is minimizing uncertainty principle, and in principle one can have h over 4. Do you know what coherent state is? Do you know that coherent states minimize Heisenberg uncertainty relation? Okay, the message is one cannot measure simultaneously coordinate and momentum with arbitrary precision. The same for spin. Since three components of spin operator are not commuting with each other, one cannot measure all three components simultaneously. But in theory of angular momentum, you know that spin operator can be constructed in the representation where, for example, we assume that Sz is diagonal. So for spin 1/2, for example, the operator Sx, Sy, and Z can be represented as sum of Pauli matrices. So for spin 1/2, we have Sz matrix -1, it's diagonal. So this is Sz, this is sigma Z, sorry, and S is equal to H sigma. Sigma x is equal to 0, 1, 1, 0, it's off diagonal, and sigma y is equal to 0, minus 1. Yeah. So then we may check that Pauli matrices satisfy these commutational relations. So one takes x is z such a way that in this representation matrix Sz will be diagonal, and for arbitrary moment Sz is quantized and takes two s plus 1 projections. So for minus s plus 1, s minus 1, s. So in total we have two s plus 1 projections. So for spin 1/2 we have 2s plus 1 equal to 2. Therefore there are two projections, plus 1/2 and minus 1. So spin is characterized discrete values of projection z. However, if S is very large, we have two S plus 1 projections, much larger than 1, and we can think that, disregarding this discreteness, that this is almost classical vector. So this is why in this approximation we can start thinking about momentum as a classical vector. Of course, today I hope, if I will not go into detail explaining to you something else, today I hope we will consider quantum mechanical situation properly and calculate partition function of quantum mechanical objects such as spin in a magnetic field. But being back to discussion of the previous lecture, what did we do? We wrote that the Hamiltonian is minus m times h. This is the Hamiltonian we will be dealing with today as well, and disregarding discretization of the momentum, assuming that m is a classical vector, we said that the z-axis is chosen along the direction of magnetic field. The length of vector m is equal to m. Therefore, in spherical coordinate system, mx is equal to m sine theta cosine phi, my is equal to m sine theta sine phi, and mz is equal to m cosine theta. So the angles theta and phi are defined in accordance to this notation. Therefore, the Hamiltonian is very simple. M is just m h cosine theta. Then, with this Hamiltonian, very simple one, we solved very simple statistical mechanical problem. Namely, we calculated the partition function, which was integral over solid angle e to the power minus h over t, because the length is fixed, and this was the first task. And then we calculated average magnetization in z direction, because the field is applied in z direction, which was 1 over z d z over d h. Let me put it this way. Although we calculated it exactly by the definition that it was z, and here integral over d solid angle m cosine theta over e to the power minus h over t. So I should probably write temperature somewhere in order to be absolutely consistent with this definition. Let me write it as d log z over and put temperature. Okay, so as a result, we obtain that our magnetization is given by formula m times function m h over t. This function, L function, is called Langevin function. Function Lx, which is cotangent hyperbolicus x minus 1 over x. So then, analyzing the properties of this function, one can easily plot it. Lx is a function of x. The function is odd function of the argument. It is equal to 0 at the origin and behaves that way. We define susceptibility. Susceptibility is n over v, limit h goes to 0, mv over h. So the magnetization is a proportionality coefficient between applied magnetic field and induced magnetization times number of spins in the system, and spins are not talking to each other. Think in this way, we arrived at a very nice formula. The susceptibility of free spins, as I said, it's a free system where every spin is independent on other spins. Is inversely proportional to temperature. One can clearly see it from here. We apply this formula, see that this function is linear. It behaves as x over 3 here. Therefore, this susceptibility, the constant, is equal to m squared over 3t times n over v. So this is how to reproduce the constant. The important moment that this is m squared, okay, and this law is known as a Curie law. Then we said, how to include effects of interaction, which in fact should be important in the system. So how to take into account the fact that spins in reality are talking to each other. We said, okay, we can do it in very smart way, namely, let's fix one spin, one particular spin. For example, this one. Let's then recall that we have a macroscopic system. So the number of spins in it is 10 to the power 23. And if we are saying that 10 to the power 23, if we pay attention on one spin and see what other 10 to the power 23 minus 1 spin are doing, we can disregard the effect of absence of this spin. Therefore, we can say that effective field in the system is equal to external field, which we denoted as H, plus some constant gamma times average magnetization created by all other spins but one. And we introduced phenomenological constant gamma, which tells us how much spins talk to each other. Next week, maybe even today, we write down some microscopic model and identify this gamma through the exchange constant in the spin interacting Hamiltonian. But for the moment, all information encoded in this simple formula, which is known as molecular field, or mean field, or sometimes Weiss field, appears to be a very powerful concept in calculation of many body effects in condensed matter. So basically, what you will learn from the theory of superconductivity the microscopic theory of superconductivity, is of course a version of mean field or molecular field. So Weiss comes from the name of a German scientist working in Strasbourg, who was first applied this method in theory of magnetism. So saying that, I'm also saying that this concept of mean field or molecular field was first developed for theory of magnetism, and the meaning of what happened is just to replace the action of all systems but one spin, but by some average magnetization. What is the consequence of this? Let's calculate susceptibility. I didn't do it that time. Let's do it now. So susceptibility in the system is n over v, limit h goes to 0, mc over temperature. So this is n over v, limit h goes to 0. Here we have m, l as a function of m, and we needed to replace h by h effective here, which is m h plus gamma average magnetization over temperature divided by h. Let's continue this line. Sorry? Sorry, h, of course. H. Let's continue this line. We use the fact that, first of all, we are in the situation of induced magnetization. So we still assume that magnetization is proportional to applied magnetic field. Therefore, if h is small, mz is also small, then, then we're allowed to apply this formula. So this is n over v, limit h goes to 0. Here we replace the Langevin function by 1/3 of its argument. It's m times 1/3 h plus gamma and z over temperature divided by h. So I will continue it here. H is equal to n over v. The first term, we can take a limit h goes to 0. There is m which is missing. I put m squared. So this is n over v, m squared over 3. 10. Fine. This is precisely the same term as we had without molecular field. Nothing is surprising, plus m squared over 3 times gamma times n over v, and here we have a limit mz over h if h goes to 0, right? But this is the susceptibility by definition. So this one is chi itself. So there is a temperature. So if I collect terms in the right hand side and left hand side, I may write down that chi 1 minus m squared gamma n over v over 3 temperature is equal to n over v m squared over 3 temperature. Or what I see here, that chi is equal to some other constant, temperature minus Tc. Where Tc is equal to m squared over 3 gamma n over v. So what we see, that susceptibility diverges at some critical temperature. What this temperature means? Let me be back now to mean field equation for Langevin function. Now we have to solve equation mz is equal to m, and let me put external field equal to 0, m magnetization times gamma over temperature. So this is how equation looks like. We can easily solve it graphically. If temperature larger than critical temperature, the equation has only trivial solution. If, however, temperature is smaller than critical one, there are two other solutions, which is nothing but that. Look, it tells us that spontaneous magnetization, namely non-trivial solution of this equation, appears in the system. Therefore, there is something which is non-zero below critical temperature and zero above. And we can say that this is not a parameter. So we have spontaneous symmetry breaking. What kind of symmetry? Rotational symmetry of a sphere. And instead of rotating freely on holes here, what we have that in magnetic field, when we lower and lower temperature, magnetic moment rotates on less and less solid angle. And if temperature is equal to 0, Langevin function is equal to infinity, and mz is equal to m, so it takes the maximum projection. So if temperature is equal to 0, we just have magnetic moment aligned magnetic field. So all magnetic moments, in fact, are aligned along magnetic field. So this is precisely that. What did we learn? That this simple semi-classical theory actually captures some necessary ingredients of magnetism, namely, it captures spontaneous symmetry breaking. It captures the fact that spontaneous magnetization appears in the system. It captures the fact that at sufficiently small temperature, all moments are aligned in one direction. Then, at temperatures equal to critical temperature, the system becomes infinitely successible to the applied magnetic field. Moreover, if temperature is smaller than critical one, the susceptibility equal to infinity. Why? Look at the definition. If temperature is smaller than critical one, then the spontaneous magnetization occurs. It means that the system is magnetized despite of absence, for example, magnetic field. So let's assume that we take magnetic field equal to 0, but system is magnetized without magnetic field. Therefore, the numerator is non-zero, denominator is 0, and the susceptibility is infinite. So sometimes people like to plot inverse susceptibility as a function of temperature, and behavior of the system is of that sort. So we in fact have a phase transition. And the law of susceptibility diverging at critical temperature and describing ferromagnets is known as the Curie-Weiss law. Unlike Curie law, which describes the susceptibility of single magnetic moment, because this law tells us we have to take susceptibility of one magnetic moment and multiply it by the concentration of magnetic moment. This is when they are all independent and not talking to each other. In contrast to this situation, we see here that if moments start to talk to each other, and the constant describing the way they are talking introduced in the theory is gamma, then the critical temperature is proportional to this gamma, and also proportional to square of magnetic moment, and also proportional to the concentration of the atoms. Okay, this is what we have done in the semi-classical theory of magnetism, and let's now solve the quantum mechanical problem with the same spirit, with the same strategy. And as far as I understand, in the lectures of Professor Muller, you discussed a little bit the concept of semi-classical theory of magnetism and maybe quantum one, but you didn't discuss susceptibilities at all. Did you?
We discussed maybe theory and something about susceptibility beyond theory and some.
But do you know what Einstein-Cernicke theory is, for example? Well, we then come to this question too. But are you familiar with this Curie and Curie-Weiss law of susceptibility? So you know it from lectures of Professor Muller. Or because Professor Muller told me that you didn't discuss susceptibility. So you discussed only magnetization. But susceptibility actually is very important quantity. First of all, it's related to some correlation function. It is a response function because it shows the response to magnetic field. But also, next week we discuss how the long-range order appears in the system when we approach from the high temperature. So what happens in the system characterized, for example, by short-range interaction between spin, and then you see that susceptibility gives you a room to introduce a correlation length into the system, which shows how many spins are correlated, and in fact the phase transition occurring in critical temperature means nothing but the correlation length is becoming comparable with the size of the system. And, although the interaction between spins is short range, so only nearest neighbor stock, nevertheless, through this interaction, many spins become correlated in the vicinity of critical temperature, and eventually all of them are correlated, and spontaneous symmetry breaking occurs. So then long-range order is formed. Okay, so the same spirit, but quantum problem, and I will be also concentrating on calculation of susceptibility. Please ask questions. If you don't understand logic, if you don't understand spirit, there are no much calculations, and everything is simple. Okay. I will keep Langevin function for the moment. So we are solving now basically the same problem. H is equal to m times H, where H is magnetic field, but what m is? M is the magnetic moment of atom, which is equal to G, J, mu Bohr times J, where J is total magnetic momentum of atom. J is equal to sum of orbital momentum plus total speed. Do you know what lambda factor is? How to sum spins? Can you give me expression? Okay. If you know, you know. Good. So this is a total momentum. So L is the sum of all orbitals Li, and S is the sum of all orbitals Si. Where we are talking about shells and orbitals of the isolated atom. And again, for simplicity, we assume now that spins sitting on the different lattice sides do not talk to each other. But in a contrast to previous version, we now saying that JZ takes 2J plus 1 projections, so minus J plus 1, J minus 1, and J. And what is also specific for the quantum mechanical momentum, that one can choose a representation where both Z operator acting in Z direction and operator J square are diagonal. So although, as I said, one cannot diagonalize, one cannot find a representation, and one cannot measure all three projections simultaneously, one nevertheless can measure Z projection and J square simultaneously, and we know from quantum mechanics that G square, this G operator square, is not equal to just maximum projection square, but equal to J plus 1. So this is, again, quantum mechanical manifestation of quantum mechanics. So now everything is written, and we are calculating average magnetization in Z direction, which is G J mu Bohr times sum of a projection from minus J to J e to the power G J mu Bohr H m over temperature, and here is a sum over m equal to minus J to J m times e to the power G J mu Bohr H m over temperature. So this is our partition function, and this is how we calculate average magnetization in Gibbs ensemble. Okay, in this general expression, let me take some example, namely, let's assume that total L is equal to 0 and total S is equal to 1/2. S is equal to 1/2, therefore J is equal to 1/2 and JZ is equal to plus minus 1/2. Then each of the sums in numerator and denominator consist of two terms. Gj mu Bohr stand in front. We have when m is equal to 1/2, we have exponent to the power Gj mu Bohr H over to temperature plus e to the power Gj mu Bohr H with sign minus over to temperature. In the numerator, we have 1/2. When m is equal to 1/2, it's equal to 1/2 e to the power Gj mu Bohr H over temperature. When m is equal to minus 1/2, we have minus 1/2 e to the power minus Gj mu Bohr H over to temperature. Or we have mz is equal to 1/2 G, well, J is equal to 1/2, let me write 1/2 mu Bohr And here we have nothing but tangent hyperbolicus G1 mu ball H over 2 times. So for spin 1/2, it's very simple, and you can already see that the function which is written on the right hand side behaves very similar to behavior of Langevin function. Namely, this is odd function of the argument. It is 0 at magnetic field equal to 0, and it is limited by 1 and minus 1. This is what you all know how to do, and I believe you calculated this function many times. Let's take spin equal to 1 in order to show that the expression is not as simple. For arbitrary momentum, but once I would like to do it, just to repeat the calculation. So if I consider the situation now that the total orbital momentum is equal to 0, but spin is equal to 1, then J is equal to 1, and Jz takes 3 projections, 1, 0, minus 1. Okay? Then Mz, in accordance to this formula, is equal to G1 mu Bohr, and again I have numerator and denominator. In denominator, I have 3 terms corresponding to 3 projections. When m is equal to 1, I have e to the power G1 mu Bohr h over temperature. When Gz is equal to 0, m is equal to 0, I have e to the power 0, it is 1. And when Gv or m is equal to minus 1, I have e to the power minus G1 mu Bohr h over temperature. So these are 3 terms standing in partition function in denominator. In numerator, I have not 3 terms but 2, because term with 0 projection will be equal to 0. Obviously. So it is e to the power G1, sorry, mu Bohr h over temperature minus, so only projection 1 and minus 1 contribute, e to the power minus G1 mu Bohr h over temperature. Okay, this is expression for average magnetization, but what one can check is that the property of the function in the right hand side of the equation are basically the same. Look, if we take h very small, then what stands in denominator is twice hyperbolic sinus. Hyperbolic sinus of small argument behaves as argument. What stands in denominator is constant. Therefore, the function is equal to 0 at h equal to 0, which can be clearly seen from here, and behaves linearly for small deviations from 0. Okay, let me make a general statement, namely that for arbitrary J, average magnetization is equal to Gj mu Bohr J times some function which I will call Bj, and this is a function of argument Gj mu Bohr J h over temperature.